using about machine learning using Python's Scikit-Learn package. So I just want to briefly go over what machine learning is. And I really like this quote that I also put in the notebook, that machine learning gives computers the ability to learn without explicitly programmed. So what we want from this robot here to cook something for us, and we don't explicitly write down how the robot can cook it, but we can teach them how to learn how to cook. So many of the algorithms will be based on these principles. So one of the tasks that require machine learning is the learning part. So what makes a 2 a 2? So we have a couple of different 2s here, and we can perfectly spot like all of these, but my DB will miss this because we can confuse this with a 3 or like this or that. So what essentially makes a 2? Which pixel orientation gives 2? So this is typical tasks of machine learning called classification, and we will talk more about that. So we can then, using classification, we can determine which discrete category that we want to put any kind of sample in this case. So as we said, we want the computer to detect what makes a 2, what makes a 9, 6, and everything. So this is one of the classical data sets called MNIST, and it's handwritten digits. Another use of using machine learning is to recognize the patterns, such as speed recognition and facial identity. And as we started to use Siri and how Siri understands us and the words that we choose to use. Another one is the recommender systems, like in order to a couple of the companies that use this, and many others, such as Amazon and Netflix. And when you purchase a product or when you watch a movie, then it gives you, okay, here are some of the movies that you can like, or here are some of the products you can also consider. So how does it learn if you buy a product that the other products can be related to? So again, machine learning goes in here. And the information retrieval, and it's very important, and we use it in every day. So when we write the course that I also took the slides from, I took the course last year. It's pretty good. It's very math intensive, but I highly recommend it if you want to use machine learning in your professional life. So it gathers a lot the information that's required, that's more relevant to what you're searching for. Also, the computer vision problems are directly related to machine learning, such as object detection and segmentation. And given an image like this, how can the computer learn what each object is? So how can we recognize the boundaries with separate objects too? Some of the robotics part, self-driving cars. How can the cars learn how to drive and keep the passengers safe? Or also flying robots, the drones became a part of our lives now. And we don't want them to go to places that they shouldn't go, so they need to learn properly where they're going. Some of the games that are currently very trendy, such as the AlphaGo that beat the world champion, I think, yeah, a year ago. So this is a classical machine learning task that we won't be covering, of course, but and many more, such as recognizing anomalies, such as credit card transactions. If you have a weird transaction, then how can the bank recognize that? Also, spam filtering, what makes an email a spam email compared to others, is also a part of machine learning, and many more. So I've talked about a lot of tasks of learning, but what are the types of learning? So we can separate them into 3 big parts. The first one is called supervised learning, and with supervised learning, we know the labels of the output. So we have, we know exactly, we have some kind of a data set that we know what the output value will be. If it's a cat or a dog, we know what that label is. So we can then do a classification or a regression that we will also talk about, which then we can output a real valued output rather than a category of cats and dogs. So this is called supervised. And the unsupervised learning comes in part when we don't know what the output is, but we want to learn from data, such as what are the structures in the data, such as like what features what features are actually talking about the same thing, what are the internal groups in the data, so they all go into unsupervised learning. And the reinforcement learning is when it's more when I talked about the AlphaGo playing games, we want to maximize the payoff. So we are doing an action and we want to pay off the ultimate price. So it's more of a, there's not much information to take, but just to maximize the final output. So today I would like to talk a little bit of different algorithms from each of these classes, such as classification, regression, and from unsupervised learning, the internal representation of the data, such as the dimensionality reduction that we heard a lot about, called PCA, and then also clustering, such as k-means. So I want to just briefly go over those in the notebook. But first, I want to start with the regression problem. So in linear regression, here is the smallest equation that we can't really see. But we are all very familiar with linear regression. We want to look at, we have a bunch of data points, and we want to fit a linear line to it. And we can then learn what the slope and the intersection and the intercept of it. So this is pretty simple. And if we want to make this a more polynomial function, then we can also add another parameter with x squared, so that, or x cubed, in order to get a nonlinear line like this. So what we essentially want with regression problems is that we have a bunch of data points that we also know the outputs of them, and we want to learn the underlying structure of this data, so that when a new data point comes, we can then accurately predict what the value of it will be. For this problem, I will be talking about a housing pricing data set from the Scikit-Learn package. So we're going to we want to minimize the error that we do when we predict the new data set and the real housing prices. So here we can see the errors that come up, and we want to minimize this, essentially. So we want the model to be complex enough to capture the underlying structure of the data, but we don't want it to be too complex, or we don't want it to be too simple. So the same data set with the previous slide, we can here see that these two, the top lines, do not really capture the underlying structure. They're too simple for this data set. However, if we increase so these are the polynomial regressions, and the m here refers to the maximum power of the parameter with the maximum power. So if we increase the power a lot, we can then perfectly fit all of the training points. However, it doesn't really capture the underlying data. And if we have a new data point that comes around here, we would be like between these 2 points, a new data point will probably be around here. But then we can predict it as like -infinity, which will increase the error function a lot, and we won't be accurate enough. And this case is called overfitting, and we want to avoid overfitting with many of the algorithms. So, and this is one of the perfect fits for this data set. So how can we avoid overfitting? I also want to talk briefly about cross-validation, where we separate a part of the data that has the labels aside as our test set, so that we don't see the test set when we are learning what the underlying structure of the data is. We learn and update our model based on the training data, and then we look for the test data and how well we can perform using this test data. And this is called leave one out cross-validation, if we just separate one part of the data as our test set. However, we can also choose different parts of the labeled data as our test set, which then we can talk about k-fold cross-validation. And here, if we have 4 different parts, then it's 4-fold cross-validation. And I will go over this in the notebooks as well. So, and here is another problem where we can take the regression problem into a classification problem. So if we have some real, if we have data points that have real outputs, but we also know that they belong to two different classes, then we can use different algorithms to separate these two classes, and also based on their values. So here, and I want to talk about the logistic regression. It's a bit tricky because the name itself refers to as if it's a regression problem, but it turns a real outputted value into a classification test. So I just want to talk about that, and it has benefits over the real regression problem when you have outliers in the data that can mess up with the decision boundary. So what logistic regression does is that it makes, so here is, given the number of hours a student spent learning for a class, will he or she pass the exam or not? So here we have some inputs about the hours of how many different people and how many hours they studied and whether they passed or not. So if you look at the points, and if you look at the points here, it's they didn't pass, and here they passed, and then the hours in the x-axis. We can't really find a decision line whether to say, okay, if you study at least like 5 hours, you're definitely going to pass. So we can't really find that boundary using that. But with logistic regression, we can then find the probability of the student passing given the number of hours that they've studied. So we will use this method for classification tasks that I will talk about. I also would like to talk about another classification algorithm that's also, again, has a linear boundary, but it's called, and its name is, maybe some of you are familiar, support vector machines, or SVMs. And what they essentially do is that it just looks at the data when we have two different classes and when they're closer to each other, and we want to have a decision boundary, and we want to separate these two. We are just basically interested in the closest points here that are called the support vectors. And we want to maximize the distance here so that we can be more accurate about where we are putting that decision boundary. And we can also give some probability of the points that are very close to this decision line. So it's a very well-used classification algorithm that I will briefly show how to do. And also, with any kind of machine learning algorithm, we need to report the performance of the algorithm. So how well can we predict? So here is a classification task, and we want to classify each image whether they are a dog or not. And here we can see that the green ones are correctly classified as dogs, and they are the true positives. However, here the red ones are the false positives, meaning that we classified them as dogs, but they're not dogs. So here, this kind of little funny bear and then the wolf here are not dogs, but we classified them as dogs. And then also the false negatives here, that we missed some of the dogs that are actually dogs. So we need to be able to have a trade-off between we don't want to have a lot of false positives or false negatives. What we want to have a trade-off, and it also depends on the task that you're using. So I will also show how to use some of the Scikit-Learn packages to report the performance of the classifier. And then one of the last tools is to use PCA, principal component analysis, which basically handles high dimensional data. So if you have a lot of dimensions in your data, and you know that some of your dimensions or your features are correlated with each other, they can dominate. If you just use them as they are, they can dominate your predictions, basically. So what we want to do is to find the underlying structure of the features and combine them in a way to remove this correlation. So then we can also have at the end we can have a new data set that captures most of the variance of the original data, but we can explain it with much less dimensions. We can also use PCA for visualization. If you plot the two PCs, it corresponds to many of the things. And it's also used in pre-processing and compression algorithms as well. Some of the intuition is that it basically just linearly combines the features, and if you have two correlated features like this, what we essentially want to do is to find the direction with maximum variance. So I don't want to go into detail of that, but this is the basic intuition of PCA. And then lastly, if I have time, I want to also talk about the k-means algorithm and how we can find, if you don't have any labels in the data, but we want to group the data into, let's say, 3 clusters here. So what k-means algorithm does is that it starts with random points, and then it finds the points that are closest to these cluster centers, and then updates the means until they converge to a point where they don't change anymore. So here's a couple of the iterations of the k-means algorithm, and then so here one of the things that we need to specify is that we say that we want to group the data set into 2, and then we separate it into 2, and the Scikit-Learn package is really easy to do that. So yeah, what I'm interested in doing in my PhD is to understand the gene function using machine learning in yeast. So what I'm looking at is deletion. What I'm looking in yeast is that I have 6 strains of each strain having a unique gene deletion. And what I'm interested in is how they affect the different organelles in the cell. So and I have 18 different organelles that I'm looking at. And what I essentially do is that if I have a compartment here, such as nucleolus, then I want to be able to look at how the nucleolus is changing its morphology if you delete a specific gene. And for that, I have a couple of different classes that I want to predict each gene deletion, whether they show a normal phenotype or a mutant phenotype. And I'm using a neural network to do that. So if you want, we can also talk about the neural networks in the future. It's pretty interesting. So now I would like to switch to the notebook. Yeah.
Wants to follow along the notebook, what you can do is go to that and so it's github.com/editor.
I think I had it somewhere. Sorry.
Actually, it's not editor, sorry.
Can you just send it to me in the Hangouts? Or?
Yeah. And so what you can do is you can get the raw version, put it into a text file, and save it as, or in your editor, and save it as an IO copy. And you can run that.
We can view it online.
Yeah, if you just like to follow along, you can view it online. They just don't have the option.
Okay, so you see.
What you would do is go to the issues, and then you can go to the link here, and then go to this link to view.
Maybe you can explain the raw thing too.
So does anyone here actually want to go through it as we go along, and then I'll explain? So you would like? Okay, so you can click the raw here, copy all of this, all the output, all that text, put it into an editor, and save that file with whatever name you'd like, .ipynb. And then when you open Jupyter Notebook, it should be available for you to run, given that you have all the packages, right? Okay, sorry, and now you can. Okay.
Okay, so I have a dark background for this, and can everyone see the board? Or?
You can zoom in a bit.
Zoom in. Yes. Okay.
I think that should be.
Is it fine? Sorry about that. I didn't think, and I don't know how to switch back because a package that I found somewhere. I have no idea. Okay, so some of the packages that I use here is that this one, the PyLab has the percentage sign, yeah, inline, and then this shows the plots at the same cell. So, and also there was another comment about matplotlib inline, so they do the same thing. And then what I'm going to use is the NumPy for the data sets, and also pandas just to briefly show, and then the Scikit-Learn, and then we can, so this one from the Scikit-Learn package, we have the data sets that I will use. So this, okay. So in this cell, now that I load the iris data set. So iris data set has 3 different species of the iris flower, and it has only 4 features. So what I just did is datasets load iris, and then I just turned this data set object into a pandas object so that we can just visualize what it's actually showing. So what I did was that in order to turn this dataset object into a pandas data frame, I just took the iris data and I combined it with the target value. And here, we are doing a classification test so that the target values are from are only 0, 1, or 2, depending on which class they belong to. And then with using the NumPy concatenate function, just C underscore, I combine all of that data. And then I'm just specifying the column names here by taking the iris feature names that refer to these 4 features here, and then the target as the name. And then I can show the pandas data frame the first 5 lines with the .head function. So here, for each sample flower, we have 4 information of some of the length and width, and then we have the class information. So what we want to do is to understand what this data looks like first before doing any other algorithm. So here, I just wanted to look at the correlations between the features and look at, and feature correlation are a big part of many of the data sets. Okay, so here from the, again, this is the, I think it's a version of this Scikit-Learn, I'm not sure, but the stats packages from SciPy. So I again took the, now I'm making a new data frame here that's called the feature correlations. And what I do is that I know there will be 4 features. So I'm just doing a 4x4, 2-for loop. I know this is not the best way, but but it just does what we are doing. So for each 2 features here, I'm just calculating the Pearson correlation using the stats package here. And I'm taking one of them and the other one. And then I'm just taking the correlation, the R correlation here, and I append it to my list. And then once I did that, and then I can just have all of the list as the first row of the pandas data frame. And then I'm doing this until I get all of the pairwise correlations here. And then I explicitly use all of the names that I have. This is probably the worst visualization ever, but it just shows us here that, of course, the diagonal correlations will be 1 because it's by itself. But if you look at the sepal and petal widths here, we have a very low correlation between the sepal length and width. However, with the petal length and width, we have a high correlation that's close to 0.96. And this will be useful when we are doing the principal component analysis too, because I will show in just a minute. So this is just a visualization, and what then I wanted to do is to see how this pairwise feature, how any 2 features are, sorry, let me put it this way. Is there any 2 features that we can just use as a classification test? So I just wanted to plot some of the different features, and this is one of the least important parts, so I don't want to go too much in detail. But what I do is I essentially just look at the sepal length and width, and I'm just plotting all of the data points depending on their class assignments. So here, if you follow that, we have the 3 different species of the flower, and then it's so difficult to see anything with this. I'm very sorry, and there's not much to do. But here, the left top one is talking about the sepal length and width, and then we can separate one of the classes perfectly well. And this is the other one is petal information, and then the others are length and width. What we want to take out from this is that we can perfectly see that this one, the red class, is coming out fairly distant from the other ones. So we know that we will have some trouble trying to classify these 2 rather than this. So this is just what I wanted to say. And then I want to talk about PCA here because it has only 4 features. That's easy to interpret what the principal components mean, essentially. So here we want to apply the PCA, and it's from the Scikit-Learn decomposition package. And then first, with any of the models that we are using, such as PCA in this case, and then the other methods, first we want to specify the model. So we just write the PCA that we imported, and then the number of components, such as 2. So we have 4 features, and we want to have 2 principal components at the end. So that's what we are specifying here. And then we are loading this model into our model parameter called PCA. I named it PCA here. And then what we want to do is that we want to fit and transform this data. So these 2 are 2 different concepts, and many of the models here have also separate fit and transform packages. So what fit does that, it learns what the data is, and then it transforms it, and then here it transforms the same data into what we want. If you want to fit a data set that's different than what you want to transform it to, then you would like to have 2 separate functions for that. But now we're only dealing with 1 data set, so we are just fitting and transforming the iris data into an iris PCA here. And sorry. And then once we do that, we can then separate again. So this is the 2 principal components that I plot here, the first principal component here and the second one here. And then we see that it represents, it's close to the other raw data sets that we can separate this class fairly well. I'm just going to pass through the visualization stuff because you can see it from the notebooks, and I want to cover more things. But also what I want to talk about with PCA is this term called explained variance. So when we transform a feature set into 1 principal component, how much of the variance in the data sets can we explain with that principal component? So we use that again from the PCA model that we use. And if you look here, it's PCA.explained variance ratio. So this is what we're interested in. And then I printed out what the first principal component explains, 92% variance of the data. And the second principal component only explains 5% of the variance in the data. So with just even 1 feature that we transformed, we can explain most of the variance in the data and build our any kind of machine learning algorithms on top of these principal components. Because if you can also go ahead and explain all of the variance in the data if that's important to you, but you also have to be aware of the noise in your data, and you don't want to explain the noise in your data when you're doing a PCA. Yes?
Do you know if there are any general guidelines about up to what like percentage of variation is well explained?
Yeah, so I mean it depends on your data set, so it's very difficult to interpret. But what I do is that I iteratively add new principal components so that I explain at least 80% of the data. And then I build my classification model. I look at my performance. I then change the amount of explained variance, and then I look if I can do better performance than that or worse. So that's how I choose how much variance I want to explain in the data. So that's one of the ways. And then, okay, so scaling the data is very important, and it's very simple, but it's also very tricky if you have missing values in your data or not. But essentially what we want to do with scaling is the same thing. We don't want, so if you have different kind of features in your data set, such as one of them is explained by meters and the other one is with millimeters. So you want to scale them in a way that the feature set that has a very high range doesn't dominate the output. So that's when you would like to use, when you want to use either a normalization or scaling or standard scaling. So the Scikit-Learn package has this great pre-processing sub-package that we can then use the standard scaler. So this is the package, this is the function, and then this is the sub-function that we fit and transform X. So what X is here, the iris data, and then the scaled one is very similar to what it's looking because many of the ranges are similar. So it was kind of pointless to do that, but I just wanted to show this is how you can scale the data. And again, with the scaling part, it's there can be some cases that you want to scale one of the data set and apply it to a new data set. So then you again have to need to separate the fit and transform functions into two different lines. So I'm just gonna skip the scaled part here. It's just basically, let me just show you. So this is just the same, and they look pretty much the same. So it was kind of pointless, but it just gives you an idea of what scaling may look like. And then the PCA part on the scaled is very much the similar. And then this is the same. And then okay, so this part seems a bit unnecessary for this tutorial, but what I wanted to talk about is that many of the classification algorithms work on binary data sets better. So if you have two classification sets, whether something is a yes or a no, or this class or that class, then we can have a decision boundary. But once we have multiple classes, then we need to have multiple decision boundaries. So it was kind of first easier to implement a classification algorithm on two classes, but then I realized that many of the packages here give us the multiple classes anyway, so this was very pointless, but I wanted to just take two of the iris classes here and do all of the other steps that I was planning on doing. So here, we can separate the two classes like perfectly well if you want, but and then here was some of the binary classification tasks I wanted to do. So, okay. What I wanted to show here is the logistic regression first, because I talked about how we, with the how many hours do you need to study in order to pass the exam or not, so the probability. So if we have two classes, let's say, then we can fit a logistic regression here. And then again, I'm using the linear model package. And then I just load the linear regression model with this LR parameter. And then I'm fitting the iris data set and the target values. So I put the two here to talk about the two classes. And then once I fit that, then I'm doing a prediction. So when I fit my data set, I want to use the new data set to predict here. So that's I'm using the same model, and then I'm using the predict function here to have my predictions. And then the score function that also comes with the model itself gives me it calculates the performance in terms of accuracy. So among the classes that I correctly classify, how accurate am I to classify the true positives and the true negatives compared to everything else? So if you use a logistic regression method, then we have perfect classification. We have 100% accuracy. But if you use a linear regression model, then it becomes a bit tricky because we want to fit a linear line, which seems like we can actually fit a linear line. And it performs really good, but not perfect. So, and what I mean by perfect is that now I want to talk about, I will talk about the overfitting part that I showed in the slides. But first, I want to switch back to multi-class classification because the Scikit-Learn package gives us this really nice tool. So, okay, Again, we are using the same linear model. We load back the data, the original data, and the target. And then now I'm using, again, the logistic regression. But then I have to specify that it's a multi-class problem. So it's multi-class. You just have to write this down, multinomial, and then the solver method can change. So it just depends on the optimization algorithm you want to use. So I don't have much to say about that. But again, we are loading this method here called LR multi, and then I fit the X and Y, the data and the target, and then I use the predict function again to predict and the score. So here with the 3 classes and the logistic regression, I can obtain 97% accuracy. So now I wanted to just experiment a little bit with the data that I transformed earlier, such as here I wanted to use one of the scaled ones that I used. So I already load the X scale from the previous cells. So when we do that, it's again the same. So it was pointless to do the scaling part. And then I also had the iris PCA data, so I just changed my input data into that. And now it's actually doing worse. So having a PCA, so we actually need all of the variance in the data to accurately classify this too. So you can also experiment with these other things. So here, such as one of the things I did was to take just the first 2 features from the original data, and then I can do, and I do much worse with just the 2 features, so 81% accuracy. Okay, but so far we just looked at all of the data, and we want to predict how well we do with all of the data. So we're actually kind of, we're not blind to the new data sets here. So that's when I want to talk about the cross-validation, and I'm using the Scikit-Learn model selection and train and test split. And this function is pretty good because it just takes here, as you can see. So we have 4 different arrays now that are generated by this function. And then we are just loading the data and then the target value. And then here, the test size, we want 40% of the data set to just put aside for the test set. And then the random state is done. Yes. So you can change this parameter with whatever you want. It can be just 2% or anything. And it will affect the performance because if you're just, right now we're only looking at 60% of the data, but maybe we have to look at more. So these hyperparameters are something to explore. And what I do is just, I want to print the shape so that I know that it's working correctly. So, and then I load, again, the same logistic regression method here. But now I'm fitting this method on the training set only. So I load the training set data and the training set labels. And then I fit this. And then now I'm predicting the new data sets that I set aside as the test set here. And I'm using them as Y prediction. And then I'm scoring, and then I'm looking at the score of how well I do with the test and the Y set. It's going to be, okay. So what this score function does is that essentially it also has this predict function here in itself. So when we load the X test, it's actually looking at the prediction of the target values of the test set, and then it's comparing it to the original value, to the actual value. So now we have 92% accuracy when we set aside 40% of the training set. So although this may seem like a lower one, but this is actually better than the previous ones because we now know how well we actually perform. So another thing that I really like using is a confusion matrix when you have multiple classes so that we can talk about the performance better. So this whole function here that you see, it just plots the confusion matrix, and I found it in Stack Overflow, so I just put it, it's a pretty nice tool to use. So what we want to do with this confusion matrix is that first I want to show the matrix and then explain it. Okay, so we can't see the labels here again. I'm very sorry, but on the x-axis, imagine that we have 3 different classes here that correspond to the actual labels. And then the labels here, and the labels on top here are the predicted labels. So just as I plotted the pandas data frame where I showed the correlations, the diagonal objects here correspond to the correct classification accuracy. So we can perfectly classify one of the classes by itself, but the other, and we can perfectly classify the others too, but we are misclassifying this class. So the third class we are misclassifying as the second class 4 out of 25, 4 out of 21 times. So this is just a nice method of which class we can use, which class we can predict better than the other ones. So just to go over this, we have the model data and then the target, the predicted target, and some class information. And then the confusion matrix is also a package that I use from Scikit-Learn matrix that you can also use. It's just an object that takes the target values and predicted ones if you have multiple classification. And then also the score comes here. So if you are interested, you can take a look. Okay, yeah.
Yes, this is when you choose the test size for that 40%, is that kind of like a ballpark, this is good, or do you usually go through different test sizes to see what's good for you?
Yeah, I mean, you can of course experiment with it. I mean, there are some papers that only publish with 2% set aside for the test set. So if you have a very small labeled data set, you might want to just set aside a smaller test set. But then the whole trade-off is that if you have a very small test set, then if you misclassify one of the things, then your performance is going to go really low. But if you have a lot of test sets, then you're not really learning the full underlying structure of the data. So it's definitely a trade-off. And yeah, I mean, it's just a try. If we just say, let's say like 20% we set aside, then we have perfect classification. So yeah, usually people start by 80, and then there's also the validation data set that is a part of the training data sets that you just use to optimize your hyperparameters, but I don't want to go into that, so we can talk about it later. Okay, so the next thing I wanted to do is the SVMs, and this is again it's again a linear classification method that I talked briefly about. And then here is another function that I'm using, the cross-validation score. I again split my data set into test and training sets, and then I'm using the SVM model here by just using the Scikit-Learn SVM package. And then here I have to specify the kernel. So the kernel here represents whether I want to have a linear decision boundary, or if I use another kernel that in a transformed space, it becomes linear, but if you transform it back to the raw data, then you have a non-linear decision boundary. So it gives us the flexibility to introduce non-linearity in our decision functions. So then again, we are doing the same thing as training, and we're taking the data set, training data and the target value, and then we fit it, we predict it, and then we print the score. And then also the nice thing about SVMs is that you don't, with the model, you don't have to specify if it's a binary or multiple classes that you're dealing with. So here, again, if you do so what we did the previous time with the, when we split this into 4, we just actually are doing one-fold cross-validation because we're setting aside 40% of one of the parts of the data. But if you want to do a cross-validation, then you have to choose different parts of the same data. So here, that's when I'm using the cross-validation score. And then with one-fold cross-validation, we have 97% accuracy. And with 5-fold, we have different accuracies. And what people usually do is to report the mean of these accuracies. Okay, so I have another data set that here, deal with the handwritten digits that I briefly talked about in the beginning. It's pretty much the same thing, so please go ahead and play around with this. I just have to skip right now. It's all of the same functions that I use, nothing different. And then I'm using the k-means clustering here, but instead, just for this time being, I can either focus on the regression problem or the TPOT package that we were talking about. So which one should I focus on?
So we can start with
Mhm. Okay. All right, so TPOT is, I also learned this new, but it's a very good package that actually finds which machine learning algorithm best fits your data set. So you have a data set, you have no idea which method is better. Is it SVM, logistic regression, any kind of different tests, but you just have to know whether you want to do a classification or regression, and that's pretty easy. So if you just look at, so here, the first one I put is the homepage of this package if you want to learn more, and then some of the examples that they go through. But what it essentially does is that it takes the raw data set, it does some cleaning and pre-processing, it selects some features, or it reduces the dimensions with PCA as we talked about, and then it tries a bunch of different models, and then it chooses the models that has the best validation here. So it just optimizes different kind of models and then picks the one that has the highest accuracy. So again, here it's like an example. The entire data set, we have multiple copies, and then we use either some polynomial features or PCA, and then we combine them. Then we recursively eliminate the features that don't explain much in the data set. And then here, the final classification for this data set is random forest classifier. Okay, so it's very easy to code as well. So you just have to download, I think, a couple of dependent packages for TPOT. But then we have two functions. So here we have the TPOT classifier, and then we have here TPOT regressor. So here we want to do a classification test. So I again load the iris data set, and then you can also export this. So what it does is that it gives you what the machine learning algorithm to use, and it just produces a Python script that you can just run with the model itself. So you want to export that file. And it's again the same thing actually. So you want to split your data set into training and test. Again, I just picked 40, doesn't matter. And then you again specify the model, and you just say TPOT classifier, and these parameters you can of course play around with. It just does this kind of iterations how many times. I really have no idea what these specifically mean, but it's a nice exploration topic. And then with this model, then we fit the training data and then the target value, and then we are printing the score here with the test set. So if you do this, we just have, okay. So it's relatively slower than many of the other things. So, oh, it's pretty slow actually. Okay, so it does some, so it splits the something. Okay, I really don't want to explain because I don't want to say anything wrong. Actually, I should have run this before. So, okay. What's different about the regressor is that it just, so here it goes through a bunch of different classification algorithms, and here it goes through a bunch of regression algorithms, and here I'm using the Boston housing prices data set to do the regression problem. And it again, just at the end, it's going to say it's this algorithm that you can use, and it has this much cross-validation accuracy. So, and it's pretty, yeah. I mean, here it's just in, again, a NumPy array. Yeah. I'm not sure if it works with the pandas data frame, but it shouldn't be difficult to convert the pandas into NumPy. So it's, again, the same exact format that I split the training and test set, and then the model is just itself, and it has a bunch of different hyperparameters. And this all depends on how much iterations you want to do in order to get the optimized algorithm. And then the rest is, again, the same. Okay, so once we're waiting for this, I can just briefly talk about something else.
So once
But
it's done, it's just going to tell us what classification.
Yes.
Is it also going to show the results of that classification?
Yeah, I mean, it's just like a model that we have done before. Let's say we have an STM model, and then we also did the score or like predictions. You can use it like right here as well. You don't need to have the script ready there, but it's just like, okay, if you're very interested in which algorithm works best for your data set, then you can take that and play around with it. But here you can use it as it is by just this model here called TPOT, right? So if you just say TPOT predict some new data set, then you will have your predictions. So that's what you care about. And okay, it's going relatively faster now. So it just separates this into 5 generations. And I think this package is using a genetic algorithm. So, okay. So it actually has a very high cross-validation score already, even with the first 33% of the iterations. So it's not, now it's like perfect classification already. And with Iris dataset, it's very tricky because I talked about like how we can separate one class and the other two are kind of merged. It's really hard to first try a bunch of classical algorithms to get a good accuracy. But with this, we will see that it's, I think it's the random forest that they found works best for it. So.
Why is it still optimized?
Yeah, and I have no idea. Right?
Why is it only
Started set to
Yes.
5 generations, so it'll go to 5 when you, so you want to be like generally higher, and then once you take that way up, it shows you the
It just needs to output which algorithm is working the best, but
There's
now
also
it's
where
kind
you
of
get
stuck.
more than just the best one. You can take to the top 5.
Yeah.
And then explore it. So maybe it'll rank all or something like that.
Yeah, so again, it still does it. But like, please take a look at these websites here that they show like a bunch of different examples and what else you can do with this. Okay, so it goes on like
So it
that.
also adds new features on the existing features. It doesn't only limit it, or
It also, so here, it also like looks at like some of the polynomials of the feature, and it also applies PCA, it combines them, and then recursive feature elimination. So if you, so how this works is, I don't know if I'm correct or not, but like you have a bunch of features and you remove one of them, you look at the predictions, whether they change the predictions at all or not, and if they don't change, you just get rid of them. So you do it recursively and like singly until you have like your feature set that's like perfect in order to explain and doesn't require anything else.
okay. And these
Yeah.
2 ways of adding features, what I'm going to say, are those the most common
I mean,
ways
this
to
is-
actually add features, or are there others that are not considered?
I'm not sure. Yeah, I don't know if like it's taking like x1 and x2 and like multiplying those two or not. Maybe it's like in one of this. Like this is just a picture that I found from the their website. So okay, so we still can't get the result, but okay. Just to actually, there's not much to say about the regression problem here, but yeah, I can't really say it too. So if you want to do a regression problem, and I think, so the Boston housing prices is a really good data set. It's complex enough, and it only has 13 features, and it has continuous values of the housing price. So I just, again, would want to show it in a pandas data frame, but I can't load it here. And what I then do is that I again looked at some feature correlations and see if I plotted some feature correlation together to see if I can, oh, sorry. So here I plotted each feature, so the 13 features, and then the value of the house and the correlations among those two. So which feature is the best to explain the target value? So that's how we can just look at that. And then I just here wanted to, okay. So now the TPOT results are out. And then here we can see that, okay, I was wrong, and it's the k-nearest neighbors classifier. That works perfect for this case, and it's cross-validation. Okay, so this one. So that was the cross-validation score, which should be something else. And then I print the actual score, and that's 91% accuracy. So it finished right now, yeah. And then it's also, oh, sorry, I don't. Okay, so. So here, so it's saved, sorry. Okay. Oh, it didn't save. All right, so you should have seen wherever you're saving the Python script, and I think I removed that part, yeah. So I commented it out. So here you can export this whole thing with using the model.export file. You can have the Python script running for with the method, with this method that's like implemented in it, and with all of the other data pre-processing steps. So whatever it did in order to get the optimized structure, they will be all listed in the Python script. So, okay. What I wanted to show with the Boston housing prices, just for a brief second, is that so you can do a linear regression as always. So here we load the data set, and then this has the target values that are here. Okay. And then here I just wanted to plot each of these correspond to one of the features, and then the Y values here are the housing prices, and then I also plotted the correlation values on top, and some of them are, so this one has 70% correlation, so it's pretty good in actually predicting the housing value, but it's just 70% of the time that is correct. So we need something better than just selecting one feature to explain. And now here, I'm using a linear regression method, and I have the Boston data, and then I'm also doing a PCA that I don't use. So here I again split my training and test set, and then I just present the results. So it's just 67%. So I can't even do better than one feature with linear regression. And then we can also try a bunch of different data sets here that I commented out. You can use the data set that has PCA transformed, and it's actually doing much worse because this, I have no explanation why it's 30%, but you can just try. And then here I just took the two features that I've seen from the previous plots here. I took the two, this one, and then the other one, this one. So this feature and this feature, I just took them, and then I see if I can do better or not. I'm doing worse. So I need all of the other variants in the other features. What I want to show with the linear regression is that maybe sometimes we want to also use regularization. So if you're familiar with it, you want to also penalize the complexity of your model too. So you can have a lasso regression, lasso regularization or ridge regularization. So this one has, they have a slight difference that I don't know how to explain right now. But once we also use that kind of regularization, with some data sets we can achieve better accuracies, but with this one we don't. So it's 61% with lasso regularization, and then with ridge, it's very similar to the normal one. So it's just something to play around with. And then, yeah, I just couldn't go over the k-means algorithm here, but we can just wrap it up, or yeah. If you have any other questions about anything, I know it was pretty fast, but.
Well, I had a question there.
Yeah.
You showed at the beginning, like the correlation among all the features
Mm-hmm.
in your data set.
Yes.
How do you know which ones to pick out, or does the software already do it on your own?
So Are you talking about TPOT or like general?
Well, like you saw at the beginning, like the pay mode is showing like the correlation between the value.
This one, right?
But like, how do you know if you take out a feature or not? Do you take it out here, or does like the library already?
So I don't take out any kind of feature here. Yeah, there are different algorithms that I'm pretty sure Scikit-Learn has at the recursive feature elimination. So that's what I was talking about. You remove one of them, you look at the predictions with the other three, and then if it's doing better or worse, I mean, if it's doing even better, then you can just get rid of it. If it's doing the same, you don't need to keep it, right? If it's not adding any kind of benefit to your predictions, you don't need to have that feature. So that's how you can use feature elimination too. But what I usually use is PCA because I don't know which features are required or not. And I usually have around 300 features that I'm dealing with. So I just do PCA, I look at the explained variance and I add how many. So the question is, so if you have 300 features, how many principal components do you need to have? So that's when I refer to the explained variance value. So, but feature elimination is a very well-used method too. Okay, thank you.